Now here they say a survey was conducted among female and male learners at a school about which type of cold drink they preferred. If they asked me, I would say Sparletta, that is Irn-Bru flavored. That's the best in business. The data from the survey is printed in the below table. So we have a juice if you are reading vertically. So A, females prefer juice. 36 males prefer juice. The total number of those who prefer juice is E. All right? This is the total number of learners that prefer juice. Now we jump. With regards to energy drinks, B learners or B females, they prefer energy drink. 54 males prefer energy drink. A total number of learners who prefers energy drinks is D. Very well. Now, when you are reading horizontally, this is the total number of females. In other words, A females prefer juice, B females prefer energy drink, but this is the total number of females. It doesn't matter what do they prefer, but C is the total number of females. And F is the total number of males. So this is a contingency table. Now, while we are still at it, I want you to realize there's a hidden intersection in between. What is this A? It's the probability that a child, or rather a learner, is a female and prefers juice. B is probability that a learner is female and prefers energy drinks. Of course, they're not really probabilities, but they're just the number of outcomes. I just wanted to make you aware of that. 36 is the number of males that prefer juice. In other words, you are male and you prefer juice. So those are the intersections of two events. So we are ready to begin. Let's listen to the first question. It says the events male and preferring juice are independent. Show that the value of E will be 84. They're giving you a hint in terms of how to approach the question. They're asking you to use the independence of events in order to answer the question they just asked you. And that's what we're going to do. So let's do that. Now, firstly, we need to find out what is the probability that a learner is male and prefers juice. Probability of male and juice. What is it going to be from the contingency table of ours? Well, it's going to be 36. But the question is 36 out of how much? Out of 210. Let's show you once again. 36 learners are males who happen to prefer juice. So that's the probability of male and juice. All right? 36 out of a total of 210. 210 is the total number of learners. Now we come for the probability of juice. Because E is the total number of learners who prefer juice. All right? Fine. So now when we look at the probability of juice, how many learners prefer juice? A total of 8 learners prefer, in fact, e-learners prefer juice. So E out of 210, they prefer juice. But the question said the probability of male and preferring juice. Okay, I see now. I see. But S36 is still fine. We also need to state the probability of a learner being a male. How many males do we have in total? We can actually find it, the number of males. It's going to be 54 plus 36. That will be the probability that a learner is male. So 36 plus 54 becomes 90. So the probability that a learner is male will be 90 out of a total of 210. So now we can use independence. We had to get those 3 facts straight. If 2 events are independent, it means that when you take the probability that a learner is male and you multiply it by the probability that this male prefers juice, you will get probability of male and juice. That's what we say. Now, what's the probability of male? We got it already. We said it's 90 over 210. And we times this by the probability of the learner prefers juice. We've got E learners who prefer juice out of a total of 210. Then we should equate this to the probability that the learner is male and prefers juice. And that will be 36 out of 210. So then how do we solve for E? Easy. In the numerator, we'll have 90E, but in the denominator, we'll have 210 squared. And we can equate this to 36 divided by 210. Then next, we just multiply throughout by 210 squared. So we get 90E on the left-hand side. On the right-hand side, we say that is 6 over 210 multiplied by 210 squared. We get 7560. And when you say 7560 divided by 90, you will get 84. So you had to be careful on this contingency table. I'm not sure if you are comfortable with them, but I know that I am not, so I'm mostly careful when it comes to the contingency tables. It's why I used to make a lot of mistakes when I was in school, as compared to the tree diagrams versus the Venn diagrams. Now they say calculate the probability that a female learner chosen at random from this group will like energy drinks. Think of that. The learner must be a female and the learner must like energy drink. Do you see that? They're asking you for B. That's what they're asking you to do. The probability of B, in other words. We know what is F. We got F as 90. And we also know what is E. So we know E and F, we can find C. And we can also find A. And then it will lead us to B. Let's do that. So the first thing we need to do is to find, you decide whether you begin with A or E. Let's say you want to begin with A. If you take A and you add it to 36, it must give you 84. So this means the value of A must be 84 minus 36, which will give you 48. Then you come back and you find C. You know F. If you take C and you add it to F, which is 90, this will be set equal to 210. So then, what is the value of C? It's 210 minus 90, which is 120. So now you know what is A, you also know what is C. Then it's now easy to find B. So if you take A and you add it to B, this will give you C, which means the value of B must be 120 minus 48. And this will give you 72. Knowing what you know then, you can now find the probability of B, which is the probability that the learner is female and prefers energy drinks. So it will be 72 over 210, which in its simplest form will be 12 over 35. You don't need to write it as a decimal. It's fine if you leave it as a fraction. Now let's look at the next one. So in this case, they say at a kiosk, 120 people buy either a cup of coffee or a bottle of water. Two possibilities, either coffee or a water bottle. The chance of rain on any given day is 75%. The probability that it will rain. The chance of a person buying a cup of coffee on a rainy day is 3 times the chance of the person buying coffee on a non-rainy day. All right? The probability of a person buying coffee on any given day is 7 over 12. Listen to that statement. On any given day, which means whether it's raining or it's not raining, the person can buy coffee. So I'll just say R prime to show that it's a complement. Do you see that? Whether it's raining or it's not raining, probability of buying coffee is 7 over 12. Now they say we need to calculate the number of cups of coffee that will be sold on any non-rainy day. Not on a rainy day, but on a non-rainy day. What is wrong with these people? But that's what they ask you to find. There are many ways, of course, of doing this. But to me, the easy way is using a tree diagram. It really appears easy for me. What is it that we are looking for at the end of the day? We want to find the number of cups that will be sold on a non-rainy day. So I'm going to define it for the examiner because it's always nice to tell the examiner where does X come from. So I'm going to say let X be the number of people who buy coffee on a non-rainy day. That is how I define my X. So that when the examiner or the marker sees the X, they understand what is what. Now I go to my tree diagram. On my tree diagram, two things can happen. Maybe it's raining on 24 August, or it's not raining. The probability that it will rain is 75%. Probability that it will not rain is 25%. Now, if it rains, two things can happen. And if it does not rain, two things can happen as well. Now, what are those two things? Well, people can either buy a cup of coffee or they can actually buy a water bottle. I'll say C for coffee and I'll say B for water bottle. Remember, you don't need to show the tree diagram. They didn't ask you to draw it. If you draw it for the examiner or the marker, there won't be a mark for it. All right? So yes, I'll say B is the water bottle, and this is my water bottle there. Now, I just said X is the number of people who buy coffee on a non-rainy day. Think of it. It's not raining, and therefore the number of people who buy coffee will be X. So then, what's the probability that coffee will be bought on a non-rainy day? It will be X over 120. So which means that the probability that a water bottle will be bought, given that it is a non-rainy day, will be 120 minus X divided by 120. You get why I'm saying 120 minus X? Because the probabilities on each branch must add up to 1. Good. But now they gave us a very important statement. They said, the chance of a person buying a cup of coffee on a rainy day is 3 times on a non-rainy day. What does that mean? It means the probability has to be 3x divided by 120 still. Which means for this one, it will have to be 120 minus 3x divided by 120. Then we can list our possible outcomes. You can do this, but sometimes they use arrows like this one, that one, that one, and that one. You decide what you prefer, whether arrows or vertical bars as I was. A vertical bar as I was doing it, I meant to say. Let's use arrows for once. Now, what am I saying here? The first possibility is it's raining and a person buys a cup of coffee. It's raining, but the person chooses to buy a water bottle. It's not raining. Nevertheless, the person is still drinking coffee. That's rather strange. No, it's not. I was drinking coffee yesterday and it wasn't raining. And of course, it's not raining and therefore the person needs water. Now, what did they give us? They gave us the probability that a person buys coffee on a random day, which means it doesn't matter whether it's raining or it's not raining. Point is, the person bought coffee. The question is asking you to move backwards. Remember in our lessons on the tree diagram, we said probability of finding coffee, of person buying coffee, will be this one times that plus this one times that. Still the same thing. So we don't need to write a formula, no. But the probability that the person buys coffee, yeah, no, I'll just say the probability of coffee equals what? Equals the probability that it's raining and the person buys coffee plus the probability that it is not raining, but the person still buys coffee. Now this one is 7 out of 12. It's given to us. What about others? Easy. We take 0.75 and multiply it with the thing, the 3x over 120. 0.75 times 3x divided by 120 plus 0.25 times what? Times x over 120. It's not raining, but you still want coffee. So it's x over 120 for the last one. Then let's simplify the right-hand side. We still have 7 over 12 here. Go to your calculator and say 0.75 multiplied by 3 divided by 120. So when I go to mine, which was given to me back in 2019, I get 3 over 160, and then I say x. Then I do the same for the 0.25. But the coefficient of x is 1. So you'll say 0.25 times 1 over 120. And this one will give you 480x. Then you add those coefficients up. You say 1 over 480 plus 3 over 160. So now you have 1 over 48, which is equal to 7 over 12. And the last step is just to multiply both sides by the, not even the LCD, but the 48. We want to destroy x, that's the whole point. So when you now say 7 over 12 times 48, you find that the value of x will be 28. So this means 28 cups will be sold on a non-rainy day. 28 people buy coffee on a non-rainy day, which means 28 cups of coffee will be sold on a non-rainy day. Many ways of doing this, but to me, this one seemed the easiest. Okay. Now let's look at the last one. This is how it reads. 8 runners compete in a race where there are no tied finishes. Oh, where there are no tied finishes. I didn't understand what does this mean. I'm only understanding it now. Imagine. It means that no people can have the same position. Like they don't win at the same time. We don't want to have 2 position 1s or 2 position 2s and so forth. Right. Bongi and Andrew are 2 of the competitors. Now the first question says, Calculate the total number of possible ways in which the 8 runners can finish the race. If Bongi finishes in a position immediately after Andrew. Listen to that. Bongi finishes in a position immediately after Andrew. Now, what I want you to realize here is we are going to form a group. That's one thing for sure. 2 people are going to be grouped together. All right? But the problem is we won't arrange those 2 people in 2 factorial ways as we used to in our lessons. No, there is now a restriction on that group. The first person must always be ahead of the other person. That's what is given to us here. So that means this group can only be arranged in one way. 1, 2, 3, 4, 5, 6, 7, 8. So we don't need that. Now, how many ways can this happen? They said if Bongi finishes in a position immediately after Andrew. Now, this is the first possibility. We can take those 2 people and put them there. All right? But the problem is Andrew has to be here and Bongi has to be there. So that means, yeah, that's the first possibility. Let's just say that. The second possibility is we can take them and put them on this position. Still, Andrew will have to be here and Bongi will have to be there. Third possibility, we can put them here. And of course, Andrew will be here and Bongi will be there. Yes, we are grouping the 2 people, but we won't arrange them in 2 factorial ways. No. Now, since they are forming one group which can be placed anywhere, the last possibility for this to happen is this one. Because Andrew is still ahead of Bongi, but they're just a single group. So you can take this as a single person and say, well, the 2 people are now one person. And now we have 7 people that we need to arrange. So the number of arrangements that are possible here will be 7 factorial arrangements. And this will give you 50, 40 arrangements that are possible. Yes, they're forming one group, but this group can only be arranged in one way. And the group now counts as a single person. So the 7 people can be arranged in 7 factorial ways. Lastly, they say to us, calculate the probability that 2 or more runners finish the race after Andrew and before Bongi. That's what they say. Can you see that this restriction was only imposed in the first question? This restriction only applies to 11.3.1. It doesn't apply to 11.3.2. How is this going to help you, what I just said? It's going to help you in your sample space. The sample space is 8 factorial, not 7 factorial. Very important. Now, 2 or more people finish after Andrew and before Bongi. So this means here we must carefully look at the positions. So this can actually happen in 6 different ways, as you will later discover. One, two, three, four, five, six. Good. One thing I told you about the counting principle and probability as a whole, it teaches you to consider possibilities. Good, 8. We are good to go. Now, this is what I mean. We need to be strict looking at the positions. This is position 1, position 2, position 3, position 4, 5, 6, 7, and 8. Now, the first case is when Andrew is on position 1 in all the occurrences. In other words, this is Andrew on position 1, all right? In all the different scenarios that we are having. Now, where is Bongi going to be? In the first case, Bongi is here because Andrew must finish first. For these 2 people at least, they must finish after Andrew. And Andrew is on position 1. But they have to finish before Bongi, which means Bongi must come after them. This is the first way in which this can happen. 2 people, right? But they said or more. So that means 3 people, 4 people finish before Bongi, 5 people finish before Bongi, and 6 people. 1, 2, 3, 4, 5, 6. Yes, 6 people finish before Bongi as well. So that means this one will have to be left out. I overcounted. But the question is this the only way in which this can happen? No, it's not guaranteed that Andrew will be on the first position every time. So that means there's another outcome as well. Let's go and explore such a possibility. So once again, we should have our positions there. How many lines did we have? 1, 2, 3, 4, 5. That means it should be 4 lines now. One, two, three, four, five, 6, 7, 8. Good. Now, Andrew can be on position 2. And now 2 people finish before Bongi and after Andrew. Andrew is now fixed on position 2. 3 people are now finishing before Bongi, 4 people before Bongi, 5 people before Bongi. Is this the only way in which this can happen? No, it's not. Let us explore another way. Consider all the possibilities because your life depends on it, or at least your marks. And let's say your marks, it's better that way. One, two, three, four, five, 6, 7, 8. Good. Now, Andrew is now on position 3. Here he was on position 2. Previously he was on position 1. And 2 people finished before Bongi. 3 people finish before Bongi, and 4 people finish before Bongi. Is this the only way in which this can happen? No, it's not. We've got yet again another possibility to explore. I'll use red on this one so that I don't have to go to the next slide. Yeah, I think 2 is fine for this one. 1, 2. 1, 2, 3, 4, 5, 6, 7, 8. What is another possibility? Andrew is now on position 4. Then where is Bongi? 2 people and 3 people. Now, do we have another possibility? Well, if you were to go and explore another possibility, that means Andrew will now be on position 5. But if Andrew is on position 5, then yes, it's still a possible possibility. We should explore that as well. But this one will only consider it on a single line. One, 2, 3, 4, 5, 6, 7. Good, 8. So now Andrew is on position 5. 1, 2, 3, 4. And Bongi is on the last position. Exactly 2 people finish before Bongi and after that. Now, what is going to happen in between? Remember, 2 people are already fixed on those positions. That means if I want to put a person here, I can choose 1 person from 6, 1 person from 5, from 4, 3, 2, and 1. 6, 5, 4, 3, 2, and 1, and so forth. Do you see that? All of them are going to give us 6 factorials. So the question is, how many factorials did we get in this case? In the first case, we've got 6 factorials. We've got 6 of them. This is 6 factorial. Is it really 6? 1, 2, 3, 4, 5. No, I'm lying. It's 5 of them. We got 5 factorials in the first case. 5 times 6 factorial. I meant to say that. In the second case, it's going to be 1, 2, 3, 4. It will be 4, 6 factorials. In the next case, we're going to have 3 of them. So it's going to be 3, 6 factorials. And here, we're going to have 2, 6 factorials. And lastly, we're going to have 1, 6 factorial. So when you add your 6 factorials up, you get 1 plus 3, that is, or 1 plus 2, that is 3. And then 3 plus 3 is 6. 6 plus 4 is 10. And 10 plus 5 is 15. So now you can say the probability will be the number of outcomes, where the number of outcomes will be 15 times 6 factorial divided by 8 factorial. So how much do you get when you press this into your nice calculator? Anyone with an idea? How much do you get when you press that? You should be able to get 15 over 56. You had to consider all the possibilities, otherwise, you won't get the right answer.